Assalamu alaikum. Welcome to this MATLAB tutorial. Today I am going to teach you how to design automatic voltage regulator model of power system using fuzzy logic controller in MATLAB Simulink software. Friends, the first requirement to apply fuzzy logic controller is that we must have the conventional automatic voltage regulator model of the power system. For your convenience, I am considering this automatic voltage regulator model of the power system as shown here. On this topic, I have already made the video, namely how to design automatic voltage regulator model of thermal hydropower plant using transfer function in MATLAB Simulink software. Therefore, if you can watch this video and apply the fuzzy logic controller in this model, then this model can be used for your master degree research or one of the PhD research objective. Now just look at the model. It may be observed that in this model we are using the PID controller. Now to get better visibility, I am going to do some other changes. First, just put your mouse cursor anywhere in the Simulink screen and start writing dashboard and press enter. You will see a blank window will appear. Bring this blank window here. Just double click on this window, a new box will open. Now click on this line which is connected with the scope. Just select it in order to see the graph and press OK. This window is basically a scope which will show directly the graph without opening the scope. Let's check the voltage graph using PID controller. Run the simulation. You can see the voltage graph is directly visible here without opening the scope. In the previous video, we discussed that its response was satisfactory, which was also obtained after several attempts. However, if you notice the graph, it still contains large overshoot and very long settling time. Therefore, its response can be further improved by using the PID tuner block available in the MATLAB Simulink. On this topic, I have already made a video, namely how to design PID controller in PID tuner using MATLAB Simulink software. In that video, the parameters of P, I and D after the tuning were obtained as shown here. Now double click on this PID controller and change the parameters of P, I and D with tuned parameters and press OK. You can see now the voltage response has improved and have zero overshoot and similar settling time than the previous graph. Now suppose we want to replace this PID controller with fuzzy logic controller. Therefore, before the implementation of the fuzzy logic controller, we must be aware about its input-output variables with their membership ranges. A simple way to know some information about the input and output ranges is to check the input and output values of the PID controller. For this purpose, just go to Simulink library, then go to sync. You can see here 2 workspace block is available. Take this block and bring it in the model. Connect this block here. Double click on this block. In the variable name, write input because this is the input to the PID controller. Similarly, to get the data for the output, just copy this block and paste it here. Connect this block here. Double click on this block. In the variable name, write output and click OK. Now just run the simulation in order to shift this input and output data from the Simulink model to the workspace. Now just right click on this input and click on plot. It will show the input graph. From this graph, it can be observed that input data range for PID controller is from 0 to 1. Similarly, just right click on this output and click on plot. It will show the output graph. From this graph, it can be observed that the output data range for the PID controller is from 0 to 8. It means now we have some idea about the input and output ranges. Therefore, let's start to design fuzzy logic controller. First, select the whole model. Copy this model and paste it here. It is because we want to design 2 models, one with PID controller and other with fuzzy logic controller. Now come to the command window. Type fuzzy and press enter. A new window will open showing the fuzzy logic controller GUI toolbox. it may be observed that by default Mamdani fuzzy inference system is set. Furthermore, we know that the Mamdani fuzzy inference system always uses centroid method for defuzzification as shown here. By default, it consists of one input, one output and the rule base. If you want to use Takagi-Sugino fuzzy inference system, then go to File, click on New FIS. Here both Mamdani and Sugino options are available. You can select Takagi-Sugino option if you want. If you want to add another input and output in the fuzzy logic controller, then go to Edit, click on Add Variable. Here input and output options are available. You may add input or output variables if you want. However, I am considering this basic one input and one output for this fuzzy logic controller. As we know that the input variable name in our case is change in voltage, therefore write here change in voltage. Similarly, the output variable name is excitation, therefore write this name here. Now we are going to put the membership functions with their ranges in the input variable. To do this, double click on this input variable. A new window will open. You can see by default this input has 3 membership functions. As we know that the input range as observed from the graph was from 0 to 1, therefore keep this range as it is. Now click on this first membership function. Suppose we choose its name as EL, which stands for extremely low. Friends, it is always better to use first and last membership function as trapezoidal membership function. Therefore, click on this window. It will show you all types of membership functions such as triangular membership functions, trapezoidal membership functions, Gaussian membership functions and many others. Just select trapezoidal membership function. As trapezoidal membership function requires 4 values, therefore put 4 values as 0, 0, 0.1 and 0.2 respectively. Similarly, select second membership function. Suppose we choose its name as VL, which stands for very low. Select it as triangular membership function and put its 3 values as 0.1, 0.2 and 0.3 respectively. Similarly, select third membership function. Assign its name as L, which stands for low. Select it as triangular membership function and put its 3 values as 0.2, 0.3 and 0.4 respectively. As we still need few other membership functions, therefore to get another membership function, go to Edit, click on Add Membership Functions, select one triangular membership functions and press OK. Now select this fourth membership function. Assign its name as N, which stands for normal, and put its 3 values as 0.3, 0.4 and 0.5 respectively. Similarly, we need another membership function. Therefore, repeat the same procedure to get another triangular membership function. Now select this fifth membership function and put its 3 values as 0.4, 0.5 and 0.6 respectively. Assign its name as H, which stands for high. Similarly, we need another membership function. Therefore, repeat the same procedure to get another triangular membership function. Now select this sixth membership function. Assign its name as VH, which stands for very high, and put its 3 values as 0.5, 0.7 and 0.9 respectively. Similarly, we need another membership function. Therefore, repeat the same procedure to get another membership function. Now select this last membership function. Assign its name as EH, which stands for extremely high. Select it as trapezoidal membership function and put its 4 values as 0.8, 0.9, 1 and 1 respectively. At this stage, the membership functions for input variable, namely change in voltage, are successfully assigned. Therefore, close this window. Now we have to assign the membership functions to the output variable, namely excitation. Therefore, double click on this excitation. A new window will open. You can see by default this output has 3 membership functions. As the output range as observed from the graph was from 0 to 8, therefore keep this range from 0 to 10 to become in safe range. Now click on this first membership function. Assign its name as EL, which stands for extremely low. Select it as trapezoidal membership function and put its 4 values as 0, 0, 1 and 2 respectively. Similarly, select the second membership function. Assign its name as VL, which stands for very low. Select it as triangular membership function and put its 3 values as 1, 2 and 3 respectively. Similarly, select third membership function. Assign its name as L, which stands for low. Select it as triangular membership function and put its 3 values as 2, 3 and 4 respectively. As we still need few other membership functions, therefore get another membership function by selecting it from edit and clicking on add membership functions. Now select this fourth membership function. Assign its name as N, which stands for normal. Select it as triangular membership function and put its 3 values as 3, 4 and 5 respectively. Similarly, we need another membership function. Therefore, repeat the same procedure to get another membership function. Now select this fifth membership function. Assign its name as H, which stands for high. Select it as triangular membership function and put its 3 values as 4, 5 and 6 respectively. Similarly, get another triangular membership function by repeating the same procedure. Now select this sixth membership function. Assign its name as VH, which stands for very high, and put its 3 values as 5, 7 and 9 respectively. Similarly, get another trapezoidal membership function by repeating the same procedure. Now select this last membership function. Assign its name as EH, which stands for extremely high, and put its 4 values as 8, 9, 10 and 10 respectively. At this stage, the membership functions for output variable, namely excitations, are successfully assigned. Therefore, close this window. Now we have to assign the rules in order to take the decisions. For this purpose, just double click on this block. A new window will open. You can see rule editor window is opened here to assign the rules. As a simple strategy, we are going to use the following rules. When change in voltage is low, then excitation should also be low, and vice versa. Therefore, based upon this assumption, select EL in the input, namely change in excitation box, and EL in the output, namely excitation box, and click on add rule. You can see this rule is added. Similarly, add all the rules as shown here. You can see all the rules have been assigned here. Now close this window. At this stage, our fuzzy logic controller is successfully designed. Now we have to save it. First, we have to export it to the workspace so that we can use it in our model. Otherwise, it will give error. To export it, go to File, click on Export, then click on To Workspace. A new window will open and ask for the name. Write any name of your choice. I choose AVR as the name and press OK. Furthermore, save it in any drive for your reference so that whenever you need, you can use it. To save it, again go to the File, click on Export, then click on To File. It will ask where you want to save it. Save it in any drive where you want. Now close this window. Just look at the workspace window. You can see AVR fish file is available here. Now go to Simulink library and search for the fuzzy logic controller block. Take this block and bring it in the model. Remove this PID controller block and connect this fuzzy logic controller block here. Double click on this fuzzy logic controller block and write the name of the fuzzy file which we have designed now. Therefore, write AVR here and press OK. At this stage, our model is completed. Now we can run the simulation to check the performance of the fuzzy logic controller. Click on this button to run the simulation and check the scope to see the response of the fuzzy logic controller. It may be observed that fuzzy logic controller response is extremely high. It means we have to reduce the range of the output in order to decrease the output. Therefore, let's try again. To do this, go to command window, type fuzzy space AVR and press enter. You can see our saved fuzzy logic controller is opened here. Double click on this excitation block and decrease the output range from 10 to 5 and press OK. Now close this window. Again export this model fuzzy to workspace as well as save this modified fuzzy in the drive where you already saved it. Friends, every time you have to export the fuzzy into workspace and save it in the drive after every modification. Now click on this run button to check the performance of the fuzzy logic controller. You can see this time the output of the fuzzy logic controller is reduced to half. It means we are going in the right direction. Friends, now we have to play with this fuzzy logic controller input and output ranges as well as with its rules to get the best response. This may take a lot of time. Sometimes it might create disappointment. Sometimes even you feel that it is not going to work anymore. However, you need to show patience because fuzzy logic controller takes a lot of time to tune. It is because we are trying hit and trial method to find the best response. That's why we have to try it again and again until we succeed. Friends, now I think it is the best time to discuss the limitation of the fuzzy logic controller. Fuzzy logic controller has the limitation that it is not an expert system by itself. It needs an expert human to assign clearly all the correct rules in order to provide the best response. If the expert gives wrong rules, then fuzzy logic controller may provide poor performance than even the PID controller. However, this is not the limitation of fuzzy logic controller itself, but it is the limitation or inefficiency of the human expert who assign the wrong rules due to the lack of sufficient knowledge. Therefore, we have to try it again and again and apply all possible rules to get the best response. Sometimes it may take days, weeks, even months to complete the task. Friends, as I have sufficient knowledge in the fuzzy logic controller and I have applied fuzzy logic controller for various applications. Despite of all these experiences and expertise, it still took 2 days for me to get the final correct output ranges and their accurate rules. The final corrected output ranges with its membership functions are shown here in this figure, whereas the final correct rules of the fuzzy logic controllers are shown here. Let's check the performance of the fuzzy logic controller on these values. For this purpose, click on this run button. You can see this time the output of the fuzzy logic controller is accurate and provides the best response as desired. Now let's compare the response of the PID controller and fuzzy logic controller. To do this, go to Simulink library and bring this multiplexer block. Connect this port with the fuzzy logic controller response and this second port with the PID controller response. Now copy this scope, paste it here and connect it with this output port. Run the simulation again to see the combined response of the fuzzy logic controller and PID controller for the same model. Double click on this scope. You can see fuzzy logic controller response is somehow better than the PID controller response. It may be further improved by adjusting the rules of the fuzzy logic controller. Friends, in this video I have discussed how to design automatic voltage regulator model of the power system using fuzzy logic controller in MATLAB Simulink software. This model can be used to complete your master degree or PhD research objectives. Furthermore, you can even write research paper from this model and you can publish it in any journal. Similarly, by repeating the same strategy, fuzzy logic controller can be implemented for any model related to any field in order to complete the master or PhD research. That's all for today's tutorial. If you like it, then don't forget to like my video, subscribe my channel and share this with all your friends so that they may also get benefit from this video. Thank you very much.